Welcome back. In this lecture, we will present another feature of nucleus that is to do with nuclear radius and density. First, one may ask, how do you measure radius of nucleus? These are extremely microscopic objects. You can't just use a scale or measure the radius, scale or something to measure the radius. So how do you do it? So the typical experiment is a very powerful experiment uh, that is used for making such measurement. They are called scattering experiments. We have already seen one such experiment involving Rutherford scattering, which resulted in the discovery of a nucleus. So, to begin with, you have to first decide what is the scattering probe that is to be used. Typically, the scattering probe should be of the order of the size of the object being probed. If the probe is much larger than the size of object, uh, it won't have an effect. So you have to choose a small enough object to small enough probe to study an object. So both should be comparable. So ordinary light has a wavelength of this order. This is too large a probe and cannot be used for measuring, for scattering experiments in the nuclear. So typically, the scattering intensity, when you say scattering intensity, means you send in a probe and the probe changes its direction, its trajectory. Okay, so that would depend upon, in this case, the scattering intensity can be considered as a function of three different probes. You can either use neutron as a probe, or a proton as a probe, or electron as a probe. Rutherford used proton alpha particles as probe to do the experiment that resulted in the discovery of nucleus. So these are three common probes that can be utilized, and they should have enough energies. Let's see why. So amongst this, proton has a disadvantage, right? So because proton is positively charged, nucleus is positively charged. So when you send in a low energy proton, they would be just repulsed. There'd be repulsive interaction. So the proton cannot actually uh, access uh, the vicinity of the nucleus. So unless the energy of proton is very high, if the energy is very high, the electric field interaction between the proton and the nucleus would decelerate the proton as the proton gets to the vicinity of nucleus, but still it may still have energy to overcome the Coulombic barrier. That is the possibility with the proton. Neutron, there is a disadvantage. First, it's not very easy to change the energy of neutron in a controlled manner because it's neutrally charged. And the second disadvantage is that the interaction between the neutron and the nucleus is not that well understood. Okay, that is, these two interact very via the Coulombic interaction. We know the form of the Coulombic interaction, but the interaction of neutrons with the nucleus is not that well understood because we still do not have a good understanding of strong nuclear forces. So one of the ideal probe is the electron. So electrons interact via a familiar Coulombic interaction. In addition, they have an attractive interaction because electrons are negatively charged and the nucleus is positively charged. So this issue of Coulomb barrier will not exist if electrons are used as a probe for scattering experiments. Which we won't go any further into the results of into how the scattering experiment are done. But we would just mention that with such experiment, we can get an idea of the radius of the nucleus. So it is also observed that the nuclear volumes scales proportionally with nuclear masses. Okay, so this seems to suggest that the nuclear density are more or less similar across different elements. Okay, so the inference from this statement is this statement. So the typical model for nuclear density is as follows. So in the middle of the nucleus, there is constant density, and there's a skin layer wherein the density decreases and goes to zero. All right. So this is a typical density profile that is utilized for describing the nuclear densities. So this can be fit to certain formula. So this is the constant density we were talking about, and other R can vary. This is the R, and so on. So this is the skin layer. So we can fit these values, and we can also see that this is going to be proportional. Let's see how we get that. So this is the constant density um, times the volume of the nucleus is going to be the mass, right? The density times volume is going to be mass. It is proportional to A, right? So if R is that density of the nucleus, so this is the overall volume. Let's assume that the nucleus is spherically shaped. That's a good approximation. This is proportional to A. Therefore, putting this together, R is proportional to A to the power of 1/3. Therefore, R can be written as some constant times A to the 1/3. So with we can fit these things, right? So we can get this R from scattering experiments, and you know the atomic mass. From this, we can by fitting it to different elements, we can get the value of R. All right, let's move on. In the next lecture, we will talk about a very important and yet important topic, which is still not completely understood. It has to do with nuclear forces and potential. Even though a lot of experiments has been done, it's still uh, some things are not understood. So we will just limit our discussion to explain few other features of nucleus. So in any case, nuclear force and potential will be the topic of discussion in the next lecture. Thank you.